Awesome. So, yes, so first of all, uh, thank you so very much for inviting me to this occasion. And I truly feel that um, I should have gone there in person. I will be talking today about the annealing route to complex magnetic phase discovery. And I am an assistant professor in the Department of Physics and Astronomy at Purdue University. I also have a joint position with Oak Ridge National Laboratory. And the research that I'm showing here is done with my student, Samar Ali, my graduate student, Akshat Jha, who is undergraduate, and Eliana Stoyanov is my undergraduate student. Guga is a graduate student. Hanjing is a graduate student. And with scientists at D-Wave and at Oak Ridge National Laboratory and at Fujitsu Research in America. So I will be talking about some of the motivations of this research that I'm doing with quantum annealing, about why is quantum annealing important and how can it lead to magnetic phase discovery. And I will show some results on chassis underline lattices and on triangular lattices. Um, and the main point that I want you to take out of this talk is that quantum annealing gives it's a completely new kid in the park, and it basically gives you really nice ideas about some of the physics that you would actually study in real experiments. So, and so with that in mind, let's talk about why are we interested? So we are interested in the spin phases of matter, and we know that spin phases of matter is extremely important for technological developments. For example, we got this magnetic memory because one day it was discovered by IBM that you can use the fact that you have ferromagnetism in materials to store memory. But ferromagnetism is just one example of a magnetic phase. There are so many other magnetic phases which we can use, and such as we can use this skyrmion lattices, we can use new phases such as spin ice and spin glass and emergent defects and domains. And we can possibly think of a world where we have spintronic materials, we have spintronic applications and devices using all these phenomena, and we are not there yet. But the discovery of these magnetic phases and their applications is very important to lead to new spintronics results. So, in order to and to give more examples, there of course there is a zoo of magnetic phases of matter, such as spin ices. There are valence bond systems. There are quantum spin liquids, and then the question is that how do we get access to all of that computationally, so that we can actually match the computational results to the experimental results, which is one of the prime bottlenecks that we have in the field, is that you can only simulate smaller systems. So, and to tell a little bit more of my background, I come from a neutron scattering background, so I am interested to always figure out what would happen when you take one of these materials and take it, let's say, to do a spectroscopy measurement, either Raman or neutron scattering or rigs, and or some kind of a spectroscopy in the lab where you can basically have electrodes attached to your sample and then you can do the spectroscopy. So let's try to understand what exactly we get when we say we do this spectroscopy, or when we measure these materials. What we finally measure is something called the magnetic scattering cross-section. And the reason why I'm saying it is because it is going to come up again and again in the talk that I'm presenting. And what we really measure is that if we have two spins, alpha and beta, in two parts of the lattice, what we finally measure is the 2-point correlation function in between those two spins. And that's the magnetic scattering cross-section that we measure in neutron scattering. But we measure very similar uh, quantities. In terahertz, we measure similar quantities in Raman. So this is the Fourier transform of the spin-spin correlation comes up again and again. And there are huge facilities in which we do these measurements, such as the high flux isotope reactor in in Oak Ridge National Laboratory. There is one in United Kingdom. That's the Rutherford Appleton Lab, and then we have the Paul Scherrer Institute and Spring 8 in Japan. And the kind of the results that we get looks brilliant. For example, there is a spin-ice compound, which is dysprosium titanate, where we essentially see excellent patterns of something called pinch points, which comes from topological all-in, all-out configuration of the spins. And then the question is that can we actually simulate results like this using the quantum computer? And that is really what got me thinking and getting me into the field. And at the same time, around in 2019, there was some excellent research which was coming out from the D-Wave group, which said that yes, you can do a lot of these, which is in a very large scale. And for example, they were looking at the phase transitions in a quantum spin glass, and they were able to find out the critical exponents at the spin glass to the antiferromagnetic phase transition. And I will explain you in more detail what all these Hamiltonians mean. So just these slides are for the motivation part of it. And then another one where they simulated the triangular lattice, and they did a toroidal boundary conditions on the triangular lattice on 1800 qubits, and they were able to see what looked to be the the vestiges of the Kosterlitz-Thouless phase transition for a certain annealing parameter. So for those of you who are familiar with the Kosterlitz-Thouless transition, you basically have the spontaneous formation of these vortices and anti-vortices, which kind of move around. And they were able to observe that directly using of my research goes to can we simulate a system which we can directly measure with neutrons or in the bulk. So to understand what is really happening in one of these quantum annealers, we need to understand what is quantum annealing. So in order to understand quantum annealing, let us first talk about what is simulated annealing, which some of you, I'm sure, know what it is. So in simulated annealing, what we have is an objective function and a variable x. And that objective function is more like an energy landscape. And what you are really trying to find is when you are solving the system, you're trying to find the ground state of that objective function. And in order to find the ground state of the objective function, what you're trying to find is the global minima of that objective function, the global minima of the energy landscape. And the way it is traditionally done is simulated annealing, and you can also use genetic algorithms, and depending on the shape of the landscape, you can do gradient descent. Most of the time it fails if you have several hills and several valleys, because what really happens is that if you just do gradient descent, type approaches, it will just get stuck in one of the local minima and you will not see the global minima. You can do something like simulated annealing, and what simulated annealing really does is that you basically have a Boltzmann factor, and that Boltzmann factor basically means that you accept or reject a solution not just on the basis of whether it is lower or higher in energy, but with a Boltzmann probability. And when you do that, you can actually have a finite probability of actually climbing up a hill and then going to the other side. So you can actually go from one valley to the other, and long and behold, the laws of statistical physics says that if you do this long enough, then you will finally reach the global minima. But the main point is that if you do it long enough, so do we have so much time? So it is a slow and uncertain process. So and that's where adiabatic quantum computing kind of started to kind of flourish. and which basically says that, look, if you make this system, so let's say that you have an energy landscape, you have an objective function which I call hx, and it is a part of a multi-level quantum system. And if you are and if your Hamiltonian is sufficiently slowly varying, it would mean that you would always be confined to that energy landscape and you will not jump across a barrier. So how slow is slow? So so the slowness is dependent on the energy gap. And so you have to be slower than the time scale of the energy gap. As long as you are slower than the time scale of the energy gap, and that comes directly from the adiabatic theorem that we have learned in our quantum 2, I believe, then what it means is that you will basically always be on that manifold where you are trying to solve your problem. There is also another issue that you have to worry about. For this entire process, your temperature should also be smaller than the gap that you have. So there are two conditions that you have to meet. Your temperature has to be smaller than the gap energy, and the second condition is that you have to be slower than the energy of the gap between, let's say, the n+1 eigenstate and the nth eigenstate, where you have actually embedded your objective function in the nth eigenstate. And then, of course, there is a requirement that you have to be able to embed your objective function on one of these manifolds. So that was actually that is exactly what these companies such as D-Wave does with the transmod qubits and QEra, which is another company from Harvard and Michel Lukin's group. They do it with neutral atoms, and so that's exactly what they do, and these various backends have different ways of doing your annealing. So, for example, what D-Wave does is that they use so one thing is that you cannot actually use a parameter to evolve the system which is in the same dimension as your objective function. So you have to use something else. You have to basically expand the number of dimensions that you have in order to access all the Hilbert space, and then and in order to do it. So in order to do that, the way D-Wave does is that they use something called the transverse field. The way QEra does is that it basically turns on and off the Rydberg blockade. So these are the various ways you could do it. Here I will be mostly presenting results from the D-Wave quantum annealer, and I'll not be talking about the Rydberg atoms or the neutral atoms. I have performed some research on Rydberg atoms on Chassis-Sunderland model, but will not be talking about that here. So the main challenge, however, that is facing us is that you have to have some kind of an annealing parameter which is orthogonal to the variables that you have in your system. And secondly, you will have to find a way to map your problem to this objective function HQ. And generally, that is what has been always the problem. Now, if you have a problem which is which is a general problem of optimization that we have, such as you are trying to optimize the portfolio, or you're trying to optimize, let's say, how a car engine would behave, or how to reach point A to point B faster, or the traveling salesman problem, then the problem is that these backends that we are talking about, such as D-Wave and QEra, they are dealing with these Ising spins, and then you will have to have a language translator to map your problem to this Ising spin language, and then again map it back. So it kind of is very time consuming. So what we are doing here is that we are, so I was actually working with magnetism, so I thought that, look, I mean, it is directly translatable, so we will use that advantage. the way these D-Wave and QRM machines work is that they use a principle called quantum tunneling. So what exactly is quantum tunneling? So as you know, that if you are actually in, if all your energy eigenstates are in one of these valleys, and then you have a potential barrier, then depending on the height of the potential barrier and the width of the potential barrier, you will always have a finite transition probability of moving from one side of the solid, one side of the potential barrier to the other. And this could be easily calculated in various ways. In fact, we had all done WKB approximation in our quantum 2 class, where we have seen how the transition probability kind of works, or the transmission probability kind of scales as a function of distance and barrier height and barrier distance. But that's exactly the principle that we will be using here, is that we will be constructing the potential landscape, and then we will be using some kind of a tuning parameter to tune this energy barrier dU, so that the solutions can pretty much flow from one potential one potential well to the other, so that it finally finds what is the global minima. So the way we will do it is that, let's say that you have an energy landscape, which I say is U, and then you have a potential barrier. So the way you can do it is that you can start your problem where you have a potential barrier completely restored, and then you allow some tunneling. So as if you have the potential barrier, and then you're suddenly making it transparent so that you can see what is on the other side of it. And then again, you will restore the barrier. But what has happened is that, since for a very small amount of time, you have allowed the barrier to kind of go transparent, you have actually, so all the entire energy landscape became transparent, which means that the system can just flow and know where it can exactly see where to end up, where is the global ground state. There is, so the way that is done, the way this tuning of this DU is done, so the way this opaque so if you have a potential barrier, you can make it high and completely opaque, or you can make it low and somewhat transparent. The way this tuning is actually done is using a transverse field, is using a transverse magnetic field, or in the case of Fujitsu and Toshiba, the way they do it is using magnetic tunnel junctions and statistical noise in magnetic tunnel junctions. There is also companies such as QERA and Cold Quanta who use Rydberg blockade to basically bring two atoms close by and far apart, and then they can tune the Rydberg blockade that way in order to kind of tune this potential barrier. So so that's what we have, and what we find is that in this way, so when you basically make this potential barriers transparent, the system can automatically flow to where the global minima is almost instantly, which means that unlike in Monte Carlo, where you have to go through several steps, here you are directly going into the global minima. So that is basically the advantage here. Now, of course, you have to realize that there is another type of annealing which is possible, where you actually allow the system to go across that energy barrier, which is actually called a diabatic or a non-adiabatic quantum annealing, where what you can also do is that you can actually take advantage of the other states. Here, you can actually allow the system to go into the upper level by doing a very fast quantum annealing, and then let it evolve there, and then maybe you will be able to tunnel back to the global minima. So you can do it in both ways. You can do it either using adiabatic quantum annealing or using diabatic quantum annealing. And so adiabatic quantum annealing is something which is being worked on quite a bit and is somewhat mature by now. while diabatic quantum annealing or non-adiabatic quantum annealing is something which is a lot of research is going on as we speak. But the most important thing is that whichever way you do it, quantum annealing actually gives you access to quantum states which are sort of impossible using just doing a classical quantum annealing, which is also something that I am personally very interested in, is magnetic phase discovery and using quantum annealing as one of the vehicles to actually do it. And so to give a little bit more background on what is exactly the difference between the classical and quantum annealing, was presented very nicely in this paper out here, is that the way classical annealing works is that you are basically slowly reducing the temperature to get to your final ground state, while in quantum annealing you are basically tuning a quantum tuning parameter, which could be something like field. And when you do that, from a crux of what I have been talking about so far is that in classical annealing, you have to go through all these barriers iteratively to get to the final energy state, while in quantum annealing, we can just tunnel right there. And this is a very powerful picture, that what this really means for you is that quantum annealing could be much faster as long as you are slow, but not too slow. As long as you're slow so that you don't go across your energy barriers too much, but not so slow that you are fast enough that you can do the calculations in a reasonable period of time. What you could do is that in just one step, unlike Monte Carlo, which is several iterative steps, here in just one step, you can go to the final energy and the ground state energy. And in this way, you can actually avoid getting stuck at the local minima. And there are many applications of these problems, as we see. There are several papers. For example, in the optimization community, you have the max cut problem, you have the KSAT, which is the satisfiability problems, the traveling salesman problem. And it has been applied in molecular dynamics, in optimizing chemical reaction, in financial risk management. In fact, I have a couple of papers using quantum annealers in financial risk management, actually. And then in supply chain optimization, and most importantly in magnetism and magnetic ground states, which is solving complicated states of Isaac problems, is something that I'm very interested in, because in my lab, I can go and make some of these Ising magnets using a furnace, and then sometimes I don't know what ground state is in there. So that is a problem that I will be talking about most. And one reason why I find that also extremely interesting for quantum annealers, and I think that is going to lead to a quantum utility earlier than all the other problems that we have here, is mainly because if you're trying to study magnetism using an Ising quantum annealer, a spin is a qubit is a spin. They are there is a very nice connection in between them. A spin is a qubit is a spin. You don't need to do any translation of your problem, any translation of the variables. They are almost exactly mapped one onto each other. So it becomes very nice vehicle for solving magnetic problems. So how exactly it is done? So here I'm going into the geometry which is used by the D-Wave machine. So in D-Wave, what happens is that you have an annealer. You basically have a chip which basically has several qubits, and the several qubits are connected with each other. And they are connected in form of a map, as we see here. This is called the Chimera architecture, which they have just retired. Right now, they have something called the Pegasus architecture, which is even more connected. I'll show you a picture of that later. But the way it works is that you have several qubits with these tiny red dots are several qubits, and each qubit is connected to other qubits using couplers. Those qubits I have put it as dots, but if you enlarge each of these dots, this is how they look. I mean, They are basically flux-coupled qubits where you have basically um, two rings, let's say, and you have a Josephson junction here. And you can actually bias the whole system using two magnetic fields, one which goes through this tiny loop and one which goes through this larger loop. So the magnetic field which goes through this tiny loop is basically so the Hamiltonian of this system is given by this term. You have some coefficients AS and BS. AS is the coefficient in front of the transverse field, which is sigma x, and BS is the coefficient in form of the Hamiltonian that you would want to solve. So this basically is completely written. This is an Ising Hamiltonian with a transverse field. So if you look at this flux-coupled qubits, this tiny loop that you see, you can apply a field on that. That is the field HI that you would have for the Hamiltonian that you are trying to solve. And these couplers that you see, here are the couplers which kind of couple two qubits. Now, these are essentially superconducting wires made of niobium. And depending on whether your niobium wire is superconducting or non-superconducting, you basically get a coupler between two qubits, or you don't get it. So you can make or break the coupler depending on whether it's superconducting or not. Not only that, you can actually tune the coupler strength going all the way from negative to positive. So you can have both ferromagnetic couplers and antiferromagnetic couplers. So that's how you do the whole system, and then you can bias the whole system, bias each qubit individually. And then you have this big magnetic field, which is this transverse field. And this transverse field is what is finally responsible for your quantum annealing. And so that's how the architecture looks. So you embed your Hamiltonian using these couplers and these fields, and then you use the transverse field to do the quantum annealing. So the model that we try to solve using this machine is the frustrated chassis-Sunderland lattice, where, as you know, in magnetic frustration, what we have is that all the bonds cannot be satisfied at the same time. So think of a tiny triangle. In a tiny triangle, if you have antiferromagnetic bonds, then there is no way you can satisfy all the three bonds at the same time, because if you form a dimer on one bond, then the other two bonds will be unsatisfied. So it leads to highly degenerate ground states, and is one of the bases of getting towards interesting states of matter. So here we are actually study the Ising chassis-Sunderland lattice, where chassis-Sunderland lattice is basically a square lattice with two bonds. One is J and J prime, shown exactly in this figure, where, as you can see, that the J is basically your square lattice, and then you have these red rungs, which are your J prime is a square lattice, and J are these red rungs. And because of those red rungs, what you form are these triangles. Can you see these triangles? And because these triangles are formed, this whole lattice is frustrated. It depends on the J1 by J2, J by J prime ratio. And as it turns out that for the Ising case, the frustration point comes at J by J prime is equal to 0.69. For Ising, it comes at J by J prime roughly equal to 1. So that's your final lattice. And the reason why we are interested in this lattice is because it is implemented in several materials. For example, the Heisenberg chassis-Sunderland model is implemented in strontium copper borate, and the Ising lattice is implemented in these tetraborides, which are researched quite a bit nowadays. So how does the data from neutron scattering or from magnetization? So if you go and take one of these materials and then you do a magnetization measurement, let's say using a PPMS, or then what you will find is that you find several, this is magnetization as a function of field, you will find several magnetization plateaus at 1/3, at 4/9, at 3/5. And that's how it will look. It will not go straight. The magnetization won't go straight and saturate. It will go through several plateaus. And if you actually sit on one of those plateaus and then you do a neutron scattering, so this is basically two reciprocal lattice directions, and this is a neutron scattering plot where dark is higher intensity and light is lower intensity. And then you take this one of these materials and do neutron scattering, then what you would see is that, so you see these rings, those rings are powder rings, so ignore them. What I want you to look at is these 4 tiny peaks that you see here, or these 5 tiny peaks that you see here. So you will see magnetization plateaus, and you will see new black peaks come up in a very symmetric fashion. That means that there is some weird ordering phenomena which is happening at those magnetization plateaus. Then the question that we were trying to ask is, can you actually see these results from a quantum device such as a quantum annealer? And so that was the crux of the question that we were trying to. So the way we did that is that we tried to embed this Chassis-Sunderland unit cell onto the chimera architecture. And the way you can, there are 2 ways in which you can do it. So the first one is called the pinwheel architecture, where you can say that, look, I will embed 1 spin onto 3 logical qubits by coupling them very strongly. So this whole thing becomes 1 spin, this becomes 1 spin, this green becomes 1 spin, the red becomes 1 spin. And then what you have is that you have this couplers right here, which are shown in gray. And you can show that you can, if you stare at it long enough, you will see that you can actually map this embedding onto the Chassis-Sunderland lattice. Well, that's not the only way you can do it. There is another way you could do it, which was actually suggested to us by Kelly Boothby, is that you can actually take some of these, somehow the colors got messed up here. But anyways, maybe in the next slide, the colors are fine. Let's see. Somehow the colors got messed up. But in this embedding, what we do is that each spin, so a green spin is actually embedded onto 4 qubits. You join those 4 qubits very strongly using superconducting bonds, superconducting connectors. So they basically behave like 1 single qubit. And that you call as your 1 spin. And the next spin is that yellow one there. The third spin is the red one there. The fourth spin is the blue one there. And then, as you would see, that there are 4 types of lattice sites in this Chassis-Sunderland model. And then you can have these 4 types of lattice sites that you can effectively embed on the quantum annealer. And these couplers are shown in, and you can actually tune the couplers in between them, which are actually shown in this gray. So you can show that this type of an embedding on the quantum annealer is topologically exactly equivalent to that of the Chassis-Sunderland model. So, so as you could see that this is a problem of graph embedding, and those who have interest in graph theory will find it quite interesting that you have a native graph and how you can embed a different problem on a native graph. And that's exactly what we have done here. There are multiple ways to embed a problem, but we choose the embedding which gives you the most symmetric connections. Something which is very important in these quantum annealers is that they are still in their infancy. So each qubit kind of behaves slightly differently. And if you have a different number of couplers on those qubits, they behave differently. So you have to be careful of those issues as we learned. And so, for example, here, every qubit that we has different numbers of couplers, and that kind of changes the local environment of these qubits and makes them behave slightly differently. And we don't like that. What we found is that this half cell embedding, so that is the tilt embedding, but then we found this half cell embedding right here, This half cell embedding, every qubit is connected to one more qubit. Every qubit has just one coupler. Every qubit that you see has one coupler. This qubit has one coupler, this qubit has one coupler, this qubit has one coupler, that has one coupler, that has one gray coupler, so on and so forth. Now, what that means is that every qubit sees the same environment around itself and is a much more symmetric embedding, which we could not ensure here. So we found that we always get better results when we do that. And again, it is a graph embedding problem. And we pursue the half cell embedding because it gives you a more symmetric graph. And when we do that, we embed these results on the debug chip, a picture of which I have here. And this is what we try to embed, this half cell embedding. And when we do that, this is how the final lattice looks. As you could see that we have embedded this half cell embedding on that entire lattice. And you see that you have some defects here and there, but that's what you see. And how does that translate to the chassis underline lattice? If we take this lattice that we have embedded and we kind of see how it would look if you look at the chassis underland, if you map it to the chassis underland lattice, this is how it looks. This is how big of a chassis underland lattice we ultimately managed to get. You can see that we have some defects because your debug chip has some defects. So we get a defective lattice. If you want to get a defect-free zone, this is where you should concentrate. So that's the reality right now, that every chip that is made has some defects here or there, or the qubits are not quite the same. There are some random fields. So how do we do this? So once we have embedded the problem, then there are several kinds of annealing procedures that we can do. The first is called the forward annealing. In forward annealing, what we do is that we tune this annealing parameter, which is S, just continuously. So we start with allowing full tunneling in between the states, and then we slowly attenuate the potential barrier with the Hamiltonian, and then we finally end up to the right configuration. And what happens is that when you start with the full tunneling, you basically let the system tunnel everywhere. Think of this as a potential landscape, and you are making the water flow. When you let the water flow by tuning your transverse field, what is happening is that you are slowly tuning your transverse field off. With what that means is that your Hamiltonian is slowly forming. But what happens is that the water will start flowing right to the lowest point in your energy landscape. So you will find the ground state finally. So you begin here and you slowly end there. So you slowly form your Hamiltonian. So you slowly form your potential landscape. But when you form it, all your solutions are already in the final ground state. So that's exactly how you do it. And it is a very fast process. It only takes nanoseconds. No iterations necessary. That is called forward annealing. You can also do something called reverse annealing, where you start with your potential barrier fully set, and then you allow some tunneling, and then you form your potential barrier back. So that is basically called reverse annealing. So you embed the problem, you pause at a certain transverse field, and then you read out your problem. And in this way, you can get to your final state. So that's called reverse annealing. And the final thing that you can do is that you can keep on doing this in a circle. You can embed, pause, read out, and feedback the results of this readout to the next step. And you can do it in somewhat of a Monte Carlo, called the quantum evolution Monte Carlo. And in that way, you can get to your ground state. So there are three ways you can actually do this annealing. And this is more of a Markov chain type annealing process. And so we tried all three of them. And I can talk more about these offline if you want. So now for the results. So let's see how what we get. So what we know is that for the Ising-Tracy-Sunderland model, one of the solutions is a 1/3 magnetization plateau. And we know that because of Dubliniak and Subir-Sachdev's results on Ising-Tracy-Sunderland model. And what it means is that if you look at the magnetization, one of the solutions should be 1/3. And what we did is that we started doing this Monte Carlo quantum annealing, where as it, what we were doing here is that we are kind of as if shaking the system between allowing tunneling and disallowing tunneling. And what we found, to our surprise, is that if you have tuned your annealing parameter correctly, so not all annealing parameters work. So annealing parameter, this S kind of determines how fast you are annealing the system and what is the frequency that you're using. And if you have set all those parameters correctly, you get to your intended solution in the very first iteration. One of the solutions is 1/3 magnetization plateau. For an annealing parameter of roughly 0.4, what we found is that we got to our solution in the very first iteration, which we thought was pretty significant, because unlike in Monte Carlo, where you need to do several iterations, which makes the system very slow, here you are going to your final solution in just one iteration, which was very nice. So we found our ground state like pretty quickly in that solution space. There were certain things that we did to deal with the boundary conditions. I'm not going into those, but let's look at the figure. So, this was the phase diagram which was proposed by Dubliniak back in this RL paper, where they found that as a function of J1 by J2, you can get to this Ising timer phase, the Neal phase. So the ferromagnetic phases on the flanks for higher magnetic field. So H is magnetic field and J1 is fixed. H is the magnetic field and J2 is something that you vary. So this is a phase diagram as a function of J2 and H with J1 fixed. So when you do that, you get all these interesting phases. You get this dimer phase where you have no ordering, but you have dimerization, and you have this 1/3 plateau phase. So what we did was that we did an annealing right along that line. So you should be able to go from the ferromagnetic phase to the 1/3 phase, through the Neal phase, back to the 1/3 phase to the ferromagnetic phase. Question is, can we see that using the D-Wave machine? And this is the result from a D-Wave chip. And what we find is that that's exactly what we see. If we look at the magnetization coming from our D-Wave chip, then we find that the magnetization basically goes from ferromagnetism to a 1/3 location to the Neal phase, where the magnetization should be 0, because in the antiferromagnetic state, the magnetization is 0, going to the 1/3 phase back to the ferromagnetic phase. But what is more important is that we can also get access to the critical points, so we know exactly where the critical phases are. So this can become a very nice vehicle to understand how to access phase diagrams and criticality in these systems. And so this is the compilation of all the runs that we did. And what we find is that when we plot the magnetization as a color plot, then we see the ferromagnetic phase, the 1/3 phase, dimer phase, the Neal phase, the 1/3, and the ferromagnetic. You see this W type of a pattern here, which is exactly what this phase diagram is. So as you could see, that we were able to exactly get the phase diagram now, but using a D-Wave quantum annealer, which is basically what we claim. But what we also see are some new phases coming up at the critical phases, which we found is quite interesting, because those are also things that we see in a real material, but theory doesn't always show it. It's quite interesting for us. And if we try and understand what is happening, so as I said, that I'm interested in neutron scattering or scattering techniques. So I'm interested in the spin-spin structure factor. And if you look at the spin-spin structure factor that we calculate out of this lattice, remember, this is a huge lattice that we had made of almost 2000 qubits, so 400 spins, 500 spins almost. So we can calculate the structure factor very accurately. And when we do that, what we find is that we can go from the ferromagnetic phase through a critical phase into this 1/3 plateau phase, where you see 4 peaks, into the Neal phase, back through a critical phase to, again, the 1/3 phase, back through a critical phase into the ferromagnetic phase. So this is basically what you see. So what you also find is that at the 1/3 phase, you see this 4 peaks exactly at the 1/3 locations. In the nil phase, you just see one peak in the half location. But what is so interesting is that at the critical phases, you see this nice ring-like patterns. And these ring-like patterns come from some kind of an extra symmetry, maybe a new one symmetry, which is coming up right at the critical point, which we found is very interesting, is that at the critical phase, you see this ring-like states. And so that was basically what we found. And we were quite interested. So one research that I'm doing is to look at this sample of holmium tetraboride, which is actually a collaboration we are having with Joe Czepleski's group in MIT. And we went forward and measured this material using neutron Laue technique, using an instrument called Corelli in Oak Ridge National Lab. And we see these 4 peaks right here. Can you see these 4 peaks? This is reciprocal lattice. And so higher intensity is more yellow. Ignore these rings. These rings come from the sample holder. But what we see are these 4 peaks. So those are exactly the type of 4 peaks. Oops. That are the type of the 4 peaks that you see in this 1/3 magnetization plateau, which is what you see here. So that's exactly one of the research that we are trying to see if that's really true. But you also get the spin motives. So DWAVE also gives you the spin motives and also the correlations between the spins, which is quite nice. So I will not go into the details of the research that I'm doing with Fujitsu because I don't have time. But all I will say is that you can also use that annular. It's a classical annular, by the way, to discover magnetic phases. We discovered a new phase such as a 5/9 plateau phase in the J1, J2, J3 model, which was not known before. So that has been published in IEEE right now. And so we can go in various, so it is actually a very powerful tool to understand phase diagrams. But what is more interesting to me is how do we understand quantum criticality is the new research that I'm doing. And what is the role of thermal and quantum fluctuations? Can we understand that using these machines? So what we were, so as you saw that, so this research, which is now published in Physical Review XQ, where what we see is that if you look at the sigma of M, which is basically the fluctuations of the magnetism, what we find is that there is more fluctuations at the critical point. So this graph, which is sigma M, is basically the sigma of the magnetism, shows that there is clearly more fluctuations right when you go from the ferromagnetic to the 1/3 plateau phase, and then from the 1/3 to the nil phase, which means that, which makes us ask the question that, is it classical fluctuations or is it quantum fluctuations? If it's truly quantum fluctuations, can we really find new ordering principles there? Can we find something which is topological, some new physics there that is very hard to find? Because these are very large lattices we can make here. These cannot be solved using DMRG very easily, right, at the fluctuating regime. So then the question is that, can we have some advantage here? So in order to do that, the new research that I'm doing, and this is unpublished work, so if you can please stop the recording, that would be nice.
Just give me 1 minute. Let's stop. All right, so Jukka is another physics faculty who works on Majorana fermions for topological computing, and he'll tell us all about his research now. Yeah. All right, Jukka, the floor is all yours. Thank you.
Thanks very much, Prame, for the invitation to speak here. And today I will start with an introduction or tutorial on how to use Majorana bound states or Majorana zero modes to do topologically protected quantum computation. And at any time, if there are questions, just shout loudly and I'll be happy to try to answer. So I think you have already heard yesterday from Prame's introduction to superconducting qubits, what qubits are. So I don't spend too much time on the very basics, but basically just as a reminder, it's a two-level system, so you have two states, let's say 0 and 1. And you can put this into arbitrary superposition of these two states. And in this talk, I will call these two states 0 and 1 rather than, let's say, spin down and spin up, mostly because we will see that these numbers 0 and 1 actually correspond to some kind of occupation number of a fermion. Yes, and once we have many qubits together, the power of quantum mechanics is that this size of the Hilbert space grows exponentially the number of qubits. We are taking a tensor product of multiple single qubit Hilbert spaces. In conventional qubits, the time evolution that we do to make these operations, for example, controlling the qubit, moving it from 1 to 0, and vice versa, they are implemented with unitary time evolution, for example, by using some microwave pulses in the case of superconducting qubits. And the key here is to try to keep this unitary. If you break unitarity, bad things can happen. For example, the qubit can decay back to its ground state. And that's actually a kind of a problem in conventional qubits. This problem is often called energy relaxation. So basically, because this one state here in this energy level diagram, this is an excited state. So as we know from thermodynamics, systems tend to decay back to equilibrium, back to the lowest energy state. So this excited state over time will typically want to decay to the ground state. And this would be a T1 energy relaxation kind of error. There is another type of error, which is called the gate error, that happens in conventional qubits. And this is the fact that we implement the qubit operations by, for example, microwave pulses. So what can happen here is that if your pulse length is not exactly what you want, if it's, let's say, too long, slightly too long, and you wanted to apply sigma x operation, you might get a small chance of actually not implementing the sigma x operation. So you may have a small residual probability of staying, in this case, in the 0 state. And this is what we call a gate error. And basically it happens when you cannot control the, let's say, the length of the microwave pulse very accurately. What we do in topological quantum computation is we try to overcome these two problems, the energy relaxation and the gate error. And one way to do this is to use a topological phase of matter. So yesterday, I believe Srijit gave an introduction to topological phases, and for example, the fractional quantum Hall state would be one example. How I define a topological phase is basically a gapped phase of matter that can have anionic excitations, which are these brown dots here. And these anionic excitations means that there is a degenerate ground state in this topological phase. And then, for example, in this energy level diagram, I have two ground states, which are 0 and 1. And because they are degenerate, there's no energy relaxation. So there's no preferred ground state because they all have the same energy. So that kind of is useful to overcome this problem of relaxation back to some unique ground state. Here we don't have any preferred unique ground state. Now, how to do qubit operations in this? Well, turns out that in certain non-abelian topological phases, if you can move these anionic excitations and you can braid them, so you move them around each other, you can implement discrete rotations in this ground state manifold. So for example, we can go from the 0 state to the 1 state. And this is nice in two ways. First one, it's because you can do qubit rotations now. The second one is that these are actually discrete rotations. So they are topologically protected. They are insensitive to the exact path that I take when I do this braiding, and therefore they are, I would say, restricted to some discrete angles. But that's also good because it means that there's no wiggle room in the angle. So you cannot get a gate error by doing this. Now there's a small problem with this that can also happen, especially in the Majorana case, as I will discuss, namely that these discrete rotations may generate a smaller set of rotations on the Bloch sphere than you would like to have. So you might not have enough freedom to do let's say complex, to prepare complex states. Okay, but this is kind of the main idea, main motivation behind topological quantum computation. And in this talk, I will focus on the Majorana, or often called Ising anion approach. So Majoranas and the Majorana-based quantum computation really stems back to Kitayev's work from 2001. So basically, the idea is to encode a qubit in these so-called non-local Majorana quasiparticles. So what these Majoranas are, so here there are two of them, gamma 1, gamma 2, they are basically half electrons. So if you have a single electron or single fermion, you can encode it into two Majoranas. So this means that if you have a pair of Majoranas, the Hilbert space will be two-dimensional. So there will be two states, 0 and 1, and these numbers correspond to the occupation number of the fermion that is in this state. And if you want to be explicit, you can write the fermion operator as something like gamma 1 plus I gamma 2. And you can check with this anti-commutation relations of the Majorana operators that the C operator is more or less a good fermionic operator. So squares to 0 and so on, which is Pauli exclusion principle. Okay, so yeah, so naively you might think that okay, now that I have two Majoranas, I have two states, and I could use this as a qubit. Now turns out that we want to actually have qubit states that all have the same number of fermions or the same number of electrons, whereas these two states differ by one fermion. And I will show later why this is the case, why we want to restrict the fixed number of electrons or fermions. Here you can overcome this problem by just taking another pair of Majoranas, which gives you another fermion. So now you have two fermions, C and D, let's say. And then you can label your states, for example, your qubit states by this 1, 0 and 0, 1. Both states have one electron in the system, so we are in the kind of fixed number of electrons, and now we can do coherent operations between these two states. Okay. And you can show that if you can move these Majoranas, so you can braid them, then you can do qubit. You can do discrete qubit rotations in this set of states. Now, how to actually realize these Majorana quasi-particles? Kitaev proposed this simple one-dimensional Hamiltonian, which is also known as a Kitaev chain. So basically here we have n sites, and we have this tight binding type model where you have nearest neighbor hopping. So this is the T term. There's some chemical potential that controls the density or the filling of this band. And finally, most importantly, there's a superconductivity term. So there's a pairing term which pairs nearest neighbors together. So it's almost like the hopping term, except we have CC instead of C dagger C. And this is p-wave pairing because it couples neighboring sites. So if you write this in the continuum limit, you get the derivative here. In this model, you couldn't have local S-wave pairing because these fermions are spinless. So if you try to write CI, CI, that's just 0 because of Pauli exclusion. So if you put this model, for example, on a circle, or you take an infinite system that's translationally invariant, and you don't put superconductivity, so you set delta to 0, you get this familiar minus t times cosine k dispersion. And then what you can show is that you turn on the pairing term, you get a topological phase. And if you're outside the band, let's say somewhere here in chemical potential, then you get a trivial band, topologically trivial band. And you can show this explicitly. There's a topological invariant that you can calculate and so on. However, there's a very nice way to see this in real space, in a finite size system. Namely, you define, you write every fermion operator in terms of the Majorana components. So you introduce for every site where I have the operator C1, for example, here, you define two Majoranas, gamma A1 and gamma B1. And then you write the fermion operator like this. By the way, on the previous slide, when I wrote CI, I missed this factor of 1/2, which I sometimes forget. What you can show is that when your chemical potential is, let's say, outside the band, these Majoranas are paired in a kind of a local way. So basically, the ground state of the system is such that these A and B Majoranas are paired on the same site as shown here. So this is kind of like the trivial dimerized phase of the SSH model that I believe Srijit has talked about yesterday in the tutorial. However, there is the other phase of the SSH model, namely, and you can show that that's the ground state when chemical potential is in the band anywhere in this green region. So in this phase, we have this opposite dimerization where the two different sites pair up like this. And then what happens is that you have these dangling Majorana modes that are at the ends of the chain that are not coupled to anything. And moreover, the system in the bulk will be a gapped phase. So there's an energy gap. And once we kind of focus on low energies, so you cannot excite above this energy gap, then you can basically ignore those bulk states and just consider it to be some kind of insulator that doesn't do anything. And once you do that, the main degrees of freedom that you actually care about are these Majorana modes, which are at the ends of the chain. There are many proposals on how to make this, how to basically implement this Kitaev model. Some of the proposals are listed here. In this talk, I'll maybe briefly just show the semiconductor nanowire approach. Not because it would be any better than any of the others, but it will be conceptually very similar to the Kitaev chain. So I can draw one-dimensional wires basically, and then I can use that as a nice concrete example to make to draw qubit devices, at least on PowerPoint. So the 1D semiconductor model basically works this way. If you take just a one-dimensional band of fermions of electrons with spin and with kind of k²/2m parabolic dispersion, you get energy band which kind of looks something like this. Once you include spin orbit coupling, you can split these bands in momentum space so that the spin down and spin up become separate. And then if you apply magnetic field, which is along the wire, you can open a gap in the middle here by mixing the spin up and spin down bands. If you apply magnetic field, which is perpendicular to this spin quantization axis. And then it turns out once you put the chemical potential into this magnetic gap, you still have these two outer states, and it turns out that this so-called helical regime behaves in many ways like a spinless one-dimensional metal. So once you induce superconductivity to this, you can hope to realize something like the Kitaev chain model. And indeed, in this picture on the right, where I have the wire now in a magnetic field, if we place a superconductor on top of this, which is shown in blue, it will induce this delta term. So there will be a delta which is non-zero here, and outside delta is 0 everywhere. And then you can get this middle region to be in a topological phase, and you will have some Majorana end modes in this system. And moreover, the bulk will be gapped, so it will be like an insulator. Yeah, and the next ingredient that we actually need for qubits is so-called Coulomb blockade phenomenon, and I will define that in a moment. So basically, it's shown here. So once we have this segment with the superconductor on top of the semiconductor that induces these Majoranas at the ends, what we can do is we can put depletion gates here that basically form tunnel barriers at the ends. This is so that this Majorana wave function wouldn't leak out of the system, because without these gates, if you think about it in this, let's say if the wire continues here and I have no superconductivity, so delta is 0, this part of the system is just a gapless system, so it has a gapless spectrum of modes, and this Majorana wave function would somehow merge into this gapless continuum, and we don't want to have that for a qubit operation. But basically what we can do is we can put depletion gate here that basically creates a potential barrier, so that this gapless continuum is not coupled to the Majorana state. And then because of this depletion gate, the wave function of the Majorana will be basically localized in this region, and same thing with the other one. Now, once you have these depletion gates, there's another thing that tends to happen, is that and that's the phenomenon of Coulomb blockade. So basically, typically once you confine electrons by insulators, you will, oops, sorry, I pressed the wrong button. Okay. Can you see the slide again?
Yes.
Okay, good. Yes, I see some nodding. Yeah, once you confine electrons by insulators, you tend to create this so-called charging energy, which is basically just a capacitive energy. So what we essentially have here in the system is a capacitor, and then a capacitor has energy, which is given by Q squared over 2C, where Q is the charge of the capacitor and C is the capacitance. Here I've put an additional ingredient, which is this backgate, where you have capacitance CG and a voltage VG relative to this semiconductor wire. And with this backgate, you can shift this charge of the capacitor. So basically, there is this shift CG VG that we can implement with this backgate. So that means that by controlling this VG, you can basically change the number of electrons. You can change Q, which is in this nanowire. Now, finally, let me write this Q variable, which was the charge. Let me write it in terms of the number of electrons. So I will, what I have done here is basically, I wrote Q equals minus E times N12 plus NSC, where this I could call N, the total number of electrons in this confined region. And this total number of electrons consists of two pieces. The first one is what I call N12, which takes value 0 or 1. This N12 is the occupation number of this non-local fermion made out of the Majoranas. So basically, we have this fermion operator, which is 1/2 gamma 1 plus I gamma 2, and then the N12 operator. Let me write it here. This would be just C dagger C. So it's the number operator for this Majorana state. Whereas this NSC, this is the number of electrons in the blue region in the superconductor. And because the blue region is a S-wave superconductor, it always has Cooper pairs. So that means that this NSC is an even number. So let's say it takes values 0, 2, 4, and so on. And actually, these two numbers, N12 and NSC, are all you need to define the state of this simple quantum system, because there's no spin. We are in this spinless regime, so so this charge is all you need to write the state. So just as an example, and maybe let me say more formally, our Hamiltonian is this, and this Hamiltonian has this combination, which is the total charge. So the Hamiltonian commutes with the N operator, with the operator of total charge, and that means that we can label the eigenstates with the fixed number of total charge. In fact, it commutes with N12 and NSC separately, so we can use these two as separate labels. So let me give an example of what the states look like. So there's a state with 0 number of electrons, and let me use a basis where I put the N12 first, and then I put the NSC. So there's a state with 0 number of electrons, which is 0, 0. And then there's state with 1 electron, which is 1, 0. Then there's a state with 2. Now we cannot put another electron to the Majorana state. So we have to use 0, 2. So we put 2 electrons into the superconductor and have the Majorana state empty. And then with 3, we can again use the Majorana state, and so on. This is how the states basically look like. And once you have these states, you can then write the energy of the Hamiltonian. So I will draw it here. The energy will depend on this Ng variable. So I can put Ng, which is just the tuning parameter. I can put it on the x-axis. And basically, what you see is once you draw this, you can fix the total number n and then draw the corresponding energy as a function of Ng. So what you see is for the n equals 0, you get a parabola which is centered at the origin, and then for the n equals 1, you get a parabola which is centered at 1, and so on. And then from this, you can from this energy level diagram, you can basically read off the ground state for every value of Ng. So I will. I have actually a nice drawing of this slide. So I will try to. I will erase all of the text now, if that's okay. But most of it will be on the slide in a nicer writing. So this is basically the energy level diagram that you get. And what you see is that for generic value of Ng, the gate charge, the ground state will be a unique state, and the ground state is given here on the bottom. And this means that this doesn't make a good topological qubit because it doesn't have ground state degeneracy, except for these fine-tuned points, which are these dashed lines, which are at half integer values. These parabolas cross, and then you have a degeneracy. But generically, apart from these fine-tuned points, you don't have a degenerate state, and it therefore would violate the first rule of making a topological qubit. But as I mentioned, we can get the topological qubit if we use 4 Majoranas. So let's see how that. And just as a remark, even though this is not a topological qubit, you can make a charge qubit, conventional kind of not topologically protected charge qubit, and we had a paper about it shown here. So it's kind of a Majorana based charge qubit. But yeah, as I mentioned before, with 4 Majoranas, we can make a topological qubit. So it's useful to go over this in a bit more detail. So as before, once we now have 2 wires and each of them has a superconductor, we will have 2 occupation numbers for the Majoranas, which are N12 and N34. Each of them can be 0 or 1. And then we have a number operator for the superconductor, and you could consider a case where there were 2 different superconductors, one for every pair of Majoranas, and then you would need 2 numbers to label the charge of the superconductor. However, in this setup, I have merged these 2 superconductors with this bridge that's shown here. This is basically kind of like a short, but it's only short in the superconductor. So the semiconductors are still separated by this potential barrier. Now, turns out that because I'm shorting this superconductor, so I'm connecting the pieces, it's enough to only use one label for the number of particles in the superconductor, because basically the Cooper pairs that live in this blue superconductor, they are delocalized over this entire blue region, so I cannot specify where exactly they are. That's what I mean by when I say a short this. So Cooper pairs can freely flow between left and right. And the charging energy that we would write in this case would be just similar to what I had before. So it's the total charge, which now consists of these 3 components, and then we subtract the gate charge and then square it. By the way, I maybe forgot to mention this EC is E squared over 2C, and it's usually called the charging energy. It's like the Coulomb energy of a single electron with this capacitance C. Okay, so now we can do the same exercise as before. So you can find out what the states are. Now we have this additional label N34, so we need to label the states N12, N34, NSC, and then what we see is that if we fix the total charge, so let me start again from total charge equals 0. So the total charge is the sum of these. So n equals 0, we'll have 0, 0, 0. And then there's another state, which is 1, 1, minus 2. Yeah, I should have maybe mentioned that I'm assuming the superconductor, this NSC number of electrons is measured from some background. Typically, there's at least 1 billion electrons in the superconductor. And when I say minus 2, I'm measuring with respect to that that background of, let's say, 1 billion electrons, which is basically determined by the neutrality of the whole system. So it's okay to have also negative numbers in the N for NSC. The one charge state, I have two options: 1, 0, 0 or 0, 1, 0. And the two state, once again, I can put 2 electrons into the Majoranas, or I can put 2 electrons in the superconductor, and I have unoccupied Majoranas, and so on. And it's very easy to convince yourself that for any fixed number of total charge, you have 2 states instead of 1 that we had previously. And this basically means that in this set of parabolas, now every parabola becomes doubly degenerate. So I will just erase some of this text. So basically, explicitly, here we now have a generic ground state degeneracy, which is equal to 2. So there are 2 states for generic value of this gate charge, which are both ground states. And these 2 states you can use as a topological qubit. By the way, how much time do I have? I think I started a little bit late. So
You can have about 20 minutes, 25 minutes.
okay, sounds good. Thanks. Okay, so this is what you can get with 4 Majoranas. And maybe as a kind of a homework question for the students, let's say I generalized this system to have m Majorana modes, and let's say this m is an even number, just because I'm always drawing pairs of them. And when I say generalize the system, you add another superconductor that goes like this, and then another wire here, 2 more Majoranas. This would be like m equals 6, and so on. So just as an exercise, it's a fairly simple exercise to find the ground state degeneracy at a generic value of the gate charge when you have some arbitrary even number of Majoranas in the system. Okay, and I hope I don't give the answer. Okay, yes, and turns out there's lots of interesting physics that you can do with these Coulomb blockaded Majoranas. For example, something called the topological Kondo effect that I have done a lot of work on. But the basic, for qubit purposes, it's enough to consider this case of 4 Majoranas, where we basically have a single qubit now. So the next step is to ask what we can do with 4 Majoranas. And by the way, regarding this question, I'm giving a talk, I believe, on Friday, so I'll give the answer then. Okay, so what can we do with this 4 Majoranas? So I will, in this last 20 minutes or so, show you how to do single qubit operations based on this 4 Majorana qubit. And now I will also go from this concrete device. I will go back to the abstraction of just having these kind of objects just floating in space. There is maybe a question you might ask when I do this abstraction. So I go back to occupation numbers of these 4 objects. I don't consider the superconductor anymore. So you might say I'm missing a quantum number, this NSC quantum number, and that's strictly speaking true. But this NSC quantum number is just any even number. So basically, it's fine to ignore it as long as I identify all states that differ by 2 electrons. So for example, I would say in this picture, I would say that the states 0, 0 and 1, 1, I would say that they have the same charge, because there's this hidden quantum number which tells you the number of Cooper pairs, and that would be 2 here and it would be 0 here. So that these 2 states have the same total charge. Okay, so as before, I can introduce fermion operators for these Majoranas, and explicitly written, this C, for example, is 1/2 gamma 1 plus I gamma 2, and D defined similarly. And as I mentioned, the Hilbert space will be, let me see if I can move this. Okay, that's better. Yeah, the Hilbert space will be for every pair we have 2 states 0 and 1, which are labeled by the occupation number of this C fermion or D fermion for the other pair, and just explicitly the states will be can be defined as following. So there's a vacuum state which we call 0, which is occupation number 0, which is annihilated by the C operator, and then there is a state 1 that I can generate from the vacuum by applying the fermionic raising operator to that state. And then, as I already mentioned, the total Hilbert space has these 4 states shown here, and in the usual way, all of these states can be generated from the vacuum, which is 0, 0, and then applying raising operators to get the other states. And as I already mentioned, if we use the Coulomb blockaded setup, then there will be a ground state manifold, which is, let's say, just consists of these 2 states that have the same total charge, and the other 2 states that have charge 2, they will be at some higher energy if we are, let's say, sitting near the bottom of this parabola. Okay, so now we can, if we focus on these two states, 0, 1 and 1, 0, we can basically measure the qubit state by measuring this number operator C dagger C. So basically, we just measure the charge of gamma 1 and gamma 2. If we can do this charge measurement, we can we know the state of the qubit precisely. So basically, this C dagger C is kind of like a sigma Z operator. More precisely, it's 2 times C dagger C minus 1, which is the sigma Z operator. So if we act with this on the 1, 0 state, we get, so C dagger C becomes 1 in that state. So we have 2 minus 1, which is 1. So it's eigenvalue plus 1. Whereas if we act on the 0, 1 state, C dagger C is 0. So we get eigenvalue, which is minus 1. So this 2 times C dagger C minus 1 is the SZ operator. And this SZ is often called parity operator or charge parity operator. We can write this sigma Z in terms of the original Majoranas. This turns out to be useful, conceptually at least. So just by taking the C operator, as I defined it earlier, you can show that this 2 times C dagger C minus 1, this is actually exactly I gamma 1 gamma 2. So maybe this is another homework exercise to show that this is the case. So what you can do is you can kind of invert this equation for C. You can solve for gamma 1 gamma 2 by using this C and C dagger, and then you can plug it into this I gamma 1 gamma 2 and show that it becomes this one, or vice versa. You can plug in this without doing the inversion. You can plug in C dagger and C and then just do the algebra to find this. Yeah, and also this I gamma 1 gamma 2, basically because gamma 1 squared is equal to gamma 2 squared, which is equal to 1, just identity operator. You can show that this SZ squared will always be minus 1. So this means that the sorry, not minus 1, but plus 1, which means that it has eigenvalues plus and minus 1. Okay, so that's my sigma Z operator. How about sigma X and sigma Y? Actually, before going to sigma X, sigma Y, let me mention that you can measure the sigma Z operator, for example, by running current in the system. So what you can do is you can connect a terminal to gamma 1 and then another one to gamma 2, and when you apply voltage V between the two, you will get current from here to the ground. And then it turns out that there's a part of that current that depends on the occupation, depends on this sigma z, on this product I gamma 1 gamma 2. Basically, it comes from the fact that electrons will tunnel to gamma 1 and they will tunnel out from gamma 2, and turns out this tunneling amplitude contains a piece that has this operator I gamma 1 gamma 2 in it. So this allows you in principle to do measurement of this sigma z operator by measuring tunneling current. This is not the only way to measure this operator. You can also, for example, use microwave measurement. So you could put a microwave, a capacitively coupled microwave resonator to this, and then apply like time-dependent voltage, and you can show that that is another way to couple to this gamma 1 gamma 2 operator. Okay, so you can measure this sigma z operator. Now in this picture on the top right, there's of course nothing special about gamma 1 gamma 2. In principle, you can measure current between any two Majorana pairs. So I could measure from gamma 1 to gamma 4, for example. You can show that this gamma 1 gamma 4 is the sigma x operator. So in this, if you write sigma x by using this C and D and C dagger and D dagger operators, you can show that it acts this way on these states. So it will basically take you from 1 0 to 0 1, and from 0 1 back to 1 0. So therefore you can identify it as the sigma x operator, and you can show that it anti-commutes with the sigma z operator as it should. Also, if you take the product of sigma x and sigma z, you are supposed to get the sigma y operator. And indeed, if we look at sigma z, so sigma z has gamma 1 gamma 2, and sigma x has gamma 1 gamma 4. So when you take their product, if I don't care about minus signs, gamma 1 will appear twice. So you will get gamma 1 squared, which is 1. And then the only thing you're left with is gamma 2 and gamma 4. So sigma y will be something like gamma 2, gamma 4. Okay, I don't have it written. Maybe it's on the next slide. Yeah, okay, it will come on the next slide. Yeah, this just repeating that in fact this measurement of sigma x means that we actually are doing like a qubit rotation, because if we measure the current from gamma 1 to gamma 4 and we get a certain result, let's say we get Sx equals +1, it means that our qubit in the sigma z eigenbasis will be in a superposition state. So I can think of this measurement not just as a as a measurement, like a boring measurement, but I can think of it as an initialization of this superposition state in the sigma z basis. So this is a way to create the superposition of these sigma z eigenstates, which is nice. And as I mentioned, sigma y will be the gamma 2, gamma 4 operator. So you can measure it by running current from gamma 2 to gamma 4. I don't know why I drew it the voltage here. So in any case, if you can do these 3 different measurements, so you can connect the voltage source to any one of these gamma 2, gamma 1, gamma 2, gamma 3, then you can do measurements of sigma x, y, and z by measuring these currents. And by doing these measurements, you can basically do projective 90-degree rotations on the Bloch sphere. So for example, if we get sigma z equals +1, we know that our qubit is in the state 1. And similarly with -1, moreover, with sigma x measurement being +1, we know that the qubit will be in this superposition state, and so on. By doing this, by doing these 3 measurements, you can get 6 different types of outcomes, which are shown here. So you can basically access these 6 points on the Bloch sphere. Once you know your measurement axis and you know your result of the measurement, you will be certain that your state will be in one of the corners of this object shown here. And this is the kind of topologically protected rotation in a way that I mentioned, namely that you cannot get, there's nothing else that you can get if you do these measurements correctly. You can only get one of these 6 different points as the outcome. So in that sense, it's like a discrete set of results without any wiggle room for an error. Basically, it stems from the fact that when you choose the measurement axis, you choose to run current to, let's say, gamma 3, and it's very difficult to make an error where you would run current, let's say, partially to gamma 3 and partially to gamma 1. That would be something where we wiggle the measurement axis by some small angle. However, there's a note here on the bottom that these discrete rotations don't cover the whole Bloch sphere, and this turns out to be a problem. You cannot do universal quantum computation with this. You need, for example, just one additional phase gate, which is this T gate. If you can do this additional T gate, then you can cover the whole Bloch sphere. So maybe in the interest of time, I will stop here and draw the conclusion. So basically, the topological qubits are designed to overcome these 2 issues with conventional qubits, namely energy relaxation and gate errors. And they overcome these issues by having ground state degeneracy and then a set of discrete rotations that one can do either by braiding or by measurement, as I showed in my example. So you do measurements, you don't actually move the Majoranas, and you can show this more generally, that by doing measurements you can do the same things that you can get with braiding. Here are some references on the bottom, and I'm happy to take questions. Thanks.
From the audience. It's very nice talk. So this is Mukul here. So I mean, I think we all appreciate that the fact that the Majorana would change the way quantum computing is believed today. But my question is related to the fact that which system do you think that one can have Majorana detected unambiguously, because that's still an issue that varies Majorana.
Yeah, that's a great question, and I will give one system that we have been looking at recently in my talk on Friday. I think all of the let's say most of the current implementations, they are based on these systems that have an interface between semiconductor and superconductor. So these will be some kind of engineered systems that are using two different materials. And it turns out that because they have two different materials, you often get disorder on the interface or somewhere else. So it's hard to make this very. And topological protection is only, it has its limits. It cannot tolerate arbitrarily strong disorder. And right now, it seems like all the implementations where people use some kind of engineered structure, they all typically have strong disorder compared to the topological gap in terms of energy scales. I think what would be really perhaps the best way to get robust Majoranas would be to use something which is intrinsically, let's say, P-wave superconductor, something that doesn't have material interfaces. So if one can come up with a way of making a system that is intrinsically topological superconductor, then I think that would be the best way, perhaps, to get really robust and clean Majoranas. For example, the fractional quantum Hall 5/2 state could be an option. Now, still with the fractional quantum Hall, the gap is too small. The 5/2 gap. So if there's some way to increase it, that would be very useful.